Good morning, everyone. I want to go over the quiz that was originally due on September 28th at midnight. We pushed it back just a little bit. These quiz stats are before the last question was graded. So those just tell us a little bit about the quiz stats for the first, for 21 out of 30 of the points. So looking at question A here, we have a compound, AX4, made from the element X, which is in group 16. So that tells us that, A is, if it's in group 16, that's like oxygen or sulfur, it's got 6 valence electrons. And X, which is in group 17, which means it's got 7 electrons. It could be something like fluorine or chlorine. And we're told that the electronegativity difference between A and X is greater than that between carbon and hydrogen. First question, how many valence electrons? So we have AX4. So that means I have 1 times 6 for A plus 4 times 7 for X. So that's 28 plus 6 is 34 valence electrons. And we see that 33% of you answered that correctly, so that's pretty good. All right, so now we figured out that we've got 36 valence electrons. The next thing we'd have to do is figure out which one's going to be the central atom. So group 16 versus group 17, that means probably the symmetry is going to favor A, and probably the electronegativity difference is also going to favor A. So 72% of you got that, so that's good. Then we're asked about doing the Lewis dot structure and coming up with a lone pair. So again, what did I say before? We have 6 plus 28, that's 34 valence electrons. So if I put things together, I've got A with 1, 2, 3, 4 X's in a Lewis dot structure. So I just used 8 of my electrons, so I've still got 26. If I look at how many I need to meet the octet rule, each X is going to need 6. 4 times 6 is 24. So we can put those 24 in like so. And at this moment, everybody has now met the octet rule, but we got 2 electrons left over. This is, clearly a case where we have an expanded octet, and those remaining electrons go on the central atom. So the correct response here was 1, which again 44% of you got, so that's not bad. Then looking at this, we have to think about the electronic geometry. So if we go up here and look at this, we've got 5 groups, of which 1 is a lone pair, right? So 1, 2, 3, 4, and then 5 there. 5 groups tells us that it's trigonal bipyramidal in terms of an electronic geometry. It is going to have a dsp3 hybridization. The fact that one of those groups is a lone pair in the trig-Bippy system, that means we get the seesaw structure. Bond angles are going to be 90, 120, and 180 still. And that structure is going to look something like this. I'll have an X up and an X down, an X going behind the page with the dashes, X with a wedge coming out of the page, lone pair on the A. The X's all have 3 lone pairs on them, like so, and that's called the seesaw structure. If you turn it sideways, you can see it looks a bit like a seesaw. So going down these next few questions, electronic geometry is going to be trigonal bipyramidal. Again, 33% of you got that. And then the orbital hybridization is DSP3. Only 17% of you got that. Then molecular geometry is seesaw, and of course you had a whole bunch of options here, and only 17% got that one right. And then we're asked about the bond angles, and 28% of you got that right. So that's good. Maybe some of you thought it was trig bippy still if you got that, and didn't get the other ones before. And now we have to answer the question, is this polar or not? So what we're going to look at here is our structure again, which I'll kind of draw. I'm going to leave the lone pairs off just to do it quickly. But we're told that these AX bonds are polar, right? So delta minus, delta plus, presumably. So we got delta minuses on all the X's. If we drew the dipole moments, I'd have one going up, one going down, one going back, and one coming back this way, which is kind of hard to render. And if I average the two of those, these two would cancel out. But these two over here add up. They sum up. And so our net dipole on this molecule is going to be something that looks like that. That would be our net dipole. The way I generally look at it is that we have the AX bond is polar, and that we have, due to the lone pair on A, there is a lack of symmetry, and that results in a net dipole. So the molecule is polar. So I'm going to point that out somehow. I think I've got that for something like 9 points. I think I had that set to, so I'm not quite sure how that was, but I'm really going to be looking for two things: that you say that the bond is polar, and you say that there's a lack of symmetry due to a lone pair. So, that you conclude that the molecule is actually polar. So I'll do that somehow, maybe 3 points each for each of those as I grade it. So anyway, just a real quick rundown on that. Hope that helps you get ready for the exam.